So we're going to start with a jovial planet. Jovial? That means happy. Um, Jovian. Thank you. Thank you. We're going to start with the Jovian planet today. If I had plugged in my USB thing, and after we get done with that, we're actually almost done with this actually, and so we'll probably get done early, and then the lab will be Wednesday lab will do their presentations. We'll do it right after the class. We won't even wait till lab starts. Because we did that on Monday. It was actually pretty awesome. so so we'll do that today too, right? All right, so we're gonna start talking about the Jovian planets today. Those Jovian planets are Jupiter, Saturn, Uranus, and Neptune, right? They're much larger than the terrestrial planets, which we knew that already from the pictures that we've seen on Monday, right? And the interesting thing about that is they're composed mainly of hydrogen and helium, right? Hydrogen and helium, mostly gases, right? The four Jovian planets are very low average density at approximately 1.2 grams per centimeter cubed, right? So that's actually super low compared to the density of the rock that like Earth is made of, for example, right? All four are thought to have rocky cores, though, composed of iron and silicates. But the more interesting thing is that it's so cold and the pressure is so different, right, on those planets that there's thick layers of like frozen methane. Like, can you even imagine methane being frozen? Like, methane is the gas that you use in your stoves when you have gas stoves, right? I mean, can you even imagine that being frozen? That's crazy how it is, right? Also, frozen ammonia, water, all found above the core. Very interesting stuff. In fact, um, there's like I think there are actually methane lakes on the moons of Saturn. Like Titan, isn't Titan the largest moon of Saturn? And it has like methane lakes. It's actually crazy. How can you have a lake like a liquid lake of methane? That's crazy. That's absolutely extreme conditions. Maybe that's why no one can live there, right? So let's talk about the formation of the terrestrial planets. Oh, we were talking about this before, how terrestrial planets get formed, right? Um, the two least massive elements, helium and hydrogen, were the most abundant when the planets started to coalesce back in 5 billion years ago, right? Which makes sense, right? These are the first two elements, hydrogen over there, helium over there, right? And 5 billion years ago, that's when they started coalesce, right? Coalesce means to come together. And then due to the heat from the sun, most of these less massive elements escape the gravitational pull of the inner planets, right? Leaving behind more of the massive elements and resulting in thick rocky cores and higher densities for the inner planets. So that makes sense, right? The inner planets are mostly made of rock and stuff because they were still being attracted by the sun's gravity, right? But since helium and hydrogen aren't as heavy as the other elements are, right? They were able to escape the gravity of the sun for the most part, right? They were able to escape the gravity of the sun for the most part and form the outer planets. And that's the reason why the inner planets are more rocky and more dense, and the outer planets are more gaseous, right? More gaseous. That's pretty cool. Okay. So talking about the formation of the Jovian planets here, the four large outer planets were far further from the sun than and therefore much colder, which I said that a second ago, right? Jovian planets retain most of their helium and hydrogen, which now surrounds the icy layers of the innermost rocky cores. As a consequence, Jovian planets have much lower density on average, right? Just restating what I said a second ago. Okay, so let's talk about the Jovian planets individually now. Jupiter is the largest planet in the solar system in both total volume and total mass. Okay, named after the supreme Roman god of the heaven because of its brightness and giant size. Right, brightness and giant size. It's about 11 times the size of Earth. Diameter is 11 times Earth's, right, and 318 times more massive than Earth. Wow, that's a big planet. That's a very big planet, right? Average density of Jupiter is 1.3 grams per centimeter cube, and Jupiter is covered in a thin layer of clouds composed of hydrogen, helium, methane, ammonia, and several other substances. I don't think we would be able to survive in that atmosphere. I don't see oxygen in there at all. All right, so I doubt we'd be able to survive that. It's a fast rotator. It takes only 10 hours to rotate. Wow, right? How long does it take for us to rotate? Exactly, 24 hours, right? So their one day for them is what? 10 hours. Anyway, here's Jupiter, right? There's Jupiter. Looks pretty violent in that atmosphere. There's the big red spot on Jupiter, right? It's actually very, very big. I think you can fit multiple Earths inside that spot, right? I'm sure this presentation has that in there somewhere. The Great Red Spot is erratic movement, shape, color, and size. Sometimes even disappear. I didn't know it actually disappeared. That's cool. And likely a huge counterclockwise hurricane-like storm lasting hundreds of years. My God, that's crazy. Which of the following is not true about Jupiter? It's the largest planet in the solar system. It's named after the Roman god of heaven. Its diameter is 11 times that of Earth's, or it takes about 24 hours to rotate. It should be much easier for everyone to scan these now, since the since the projector is so much higher than the other one. All right. So the answer here is what? 24 hours? That's not right. How many hours is it supposed to be? 10 hours, exactly. All right, so let's talk about Saturn now. So Saturn is special. Its distinctive system of three prominent rings makes it very special. And these rings are actually inclined to the orbital plane by 27 degrees. Like it's actually tilted like this, like pretty bad, right? I mean, it's not bad, but pretty a lot, right? 27 degrees. The rings are thought to be composed of ice and ice-coated rocks that are about 10 meters. It's a big rock, right? 10-meter rock, that's huge. It's like a boulder. The most spectacular sight can be viewed from Earth uh, with a small telescope, which I've actually done that before, so that's kind of neat. The diameter is 9 times Earth and 95 times the mass of Earth. Wow, good stuff. And its density is actually really low. That's actually lower than water, right? Because remember, density of water is 1, right? And so this density is 0.7. So it's super not dense compared to water, right? So here's Saturn, right? Here's Saturn, and it's hard to see here, right? Well, see, there's Mars, there's Venus, there's Earth and the Moon right there. Pretty hard to see, right? I feel like these were taken by the Voyager space probe because you're kind of looking at Saturn and seeing all the stuff behind Saturn, Mars, Venus, and the Earth and the Moon. But the thing I want you to see here is the name of the rings, right? We have the C ring here, the B ring, and the A ring, right? And then this is called the Cassini division, and this here is called the uh, ENAC gap. ENAC gap. That's really weird. I don't know what that is, but that's interesting stuff, right? I didn't even know they had named the rings with those things. But yeah, I thought the Cassini division was interesting because there's plenty of NASA things that are named after Cassini. So, all right, next planet is Uranus, right? And it was discovered in 1781 by William Herschel. So named after Uranus, which is the father of Titans and the grandfather of Jupiter. Interesting, interesting. It has one thin ring system composed of boulder-sized particles. Well, do you even call it a boulder anymore? I mean, do you even call it a particle anymore if it's a boulder size, right? With very little, with very little dust size, right? So average density there is just above water density, 1.3 grams per centimeter. Interesting stuff. Interesting stuff. So here's a picture of Uranus. Unlike other planets, Uranus revolves around the sun on its side, and it rotates in a retrograde fashion, right? So that's one of those planets that that like that goes around the sun in one direction, but then rotates the opposite direction, right? Interesting stuff, right? And then it's actually sideways, right? That's really cool that it's actually sideways when it's going around the sun. Good stuff. I wonder why you get like a different color, like a green color there. They must have different filters that give you different wavelengths, you know? So that's kind of neat. Neato mosquito. Here's your next question. Which of the following is not true of the rings of Saturn? Right? The rings of why did I capitalize the rings of Saturn? Is that something special? I have no idea. Distinctive system of three prominent rings. The rings are inclined 27 degrees. The rings are thought to be composed of ice and ice-coated rocks. Or all these are true. All these are true. All right. All the answers here are true. Is that what everybody got? Right? I gave you plenty of time to sign in. Right. So let's talk about Neptune now. Neptune was discovered in 1846 by Johann Galle, a German astronomer, Englishman John Couch Adams, and Frenchman UJJ Leverrier. were mathematicians using Newton's law of gravitation. They noted that Uranus's motion was disturbed and predicted the location of another planet. This is now, this is how Gall eventually discovered Neptune. I see. Apparently, Neptune used to be, they used to think that Neptune was a part of Uranus, right? And then they saw that there was some weird math going around, Adams and Leverrier, right? Using Newton's law of gravitation, which we talked about at nauseum at the very beginning of the semester, right? And seeing that there was the discrepancy there, right? Gall then eventually found and discovered Neptune from that. That's pretty neat, right? Hey, there's a planet. Can I name it Neptune? That's cool. I want to name a planet. Neptune has also a large dark spot similar to Jupiter and was thought to be the result of large wind systems. Neptune and Uranus are similar in size and their compositions and their atmospheres. In many respects, these two planets can be considered twins, right? Probably fraternal twins, though, because they look very different. So fraternal twins. Think of it like that, okay? All right, so here's Neptune. Oh, yeah, see, there's a big spot there. There's also a big spot there, too. Wow, Neptune's cool. All right, cool picture of Neptune there. All right, so those are all the planets. Sadly, right? There's no talk of Jupiter, of Pluto here because Pluto's not a planet anymore. Okay, so the designation of celestial bodies, right, by the International Astronomical Union, right, in 2006, the IAU adopted the following criteria for all the solar system bodies to be a planet, right? And so the first criteria for something to be a planet by the IAU was that it must orbit the sun, right? The second thing is that the second criteria is that it must have sufficient mass for self-gravity to form a nearly round shape, right? And the very last thing here is that it must be a dominant body within its own orbit. And for some reason, we're about to learn what that reason is. This is the reason why Pluto, my favorite planet, I just said that today. I've never ever said that Pluto is my favorite planet before until today. But my favorite planet, Pluto, here, your friend of mine, gets disqualified as being a planet, right, because of the last statement. So I will ask you a question on the exam about that. I will ask you literally, right, which of the three is the reason why Pluto was disqualified as a planet? Okay, because I'm very bitter about that. Just today, though, I'm bitter about that. Okay, just today. All right, so since it's not a planet anymore, we're gonna call it now a dwarf planet. Okay, and the reason why Pluto's orbit actually takes it inside that of Neptune's orbit, right? So for that moment, Pluto is no longer dominated by its own orbit, is it? What is it dominated by? Neptune's orbit. God, that sucks. Just for that one moment, right? It's like it's like you're driving your car with your friend, right? And then your friend leaves, and then for some reason, since he was in your car, right, he gets to own your car. That's messed up, right? I was about to say a much more strong word there, but then I would have had to clip it out. But that's still messed up, right? So so that's another thing you got to remember too, right? This is the reason why. Okay, this is the reason why Neptune was just sitting in Pluto's car for a very momentary amount of time, and somehow now Pluto's no longer a planet, right? So the IAU dwarf planets are one of these categories, right? And so Pluto, along with Ceres and Eris, are now designated dwarf planets, which I didn't even realize. I didn't even know that these are planets, until recently. Dwarf planets, rather. So let's talk about the first dwarf planet from the sun. It actually sits in a Ceres. It actually sits between Mars and Jupiter, right? Wow, that's a tiny little guy. It's so small that the picture is pixelated, so you had to zoom in, right? So it lies in the asteroid belt between Mars and Jupiter. By the way, if you didn't know that, there is an asteroid belt that surrounds the inner planets. Okay, um, and so it lies in the asteroid belt between Mars and Jupiter, right? It was discovered in 1801 by Giuseppe Piazzi, right, and named after the Roman goddess of agriculture, right? Its diameter is only 940 kilometers, and that's the smallest dwarf planet, right? 940 kilometers. That's actually really small, So that's really small. Anyway, the second dwarf planet is Pluto, right? The second dwarf planet is Pluto, from the sun and beyond Neptune, right? Named for the god of outer darkness, which kind of makes sense. Anyway, So named for the god of outer darkness, its average density is only 1.6 grams per centimeter cube, right? It was discovered by Tombaugh, C.W. Tombaugh in 1930, while he was investigating discrepancies in the orbital path of Neptune and Uranus, right? It does not resemble either a terrestrial planet or a Jovian planet. Interesting. Maybe that's another reason why it doesn't fit. But yeah, it doesn't fit in as a Jovian planet or a terrestrial planet. That's interesting. And Pluto has not been visited by a space probe, only flyby, planned in 2015. Wow, interesting. Very interesting. And then a little bit more about Pluto, a little bit more. There are similarities between Pluto and Triton, one of Neptune's moons, right? Not to be confused with Titan, which is one of Saturn's moons. Okay. Some of scientists believe that there are both large asteroids that are captured from interplanetary space, right? So if this is the case, Pluto has maintained its own orbital path, and Triton was captured by Neptune. Oh, see, they were thinking that Pluto, could have been a moon, but since it's got its own orbital path, it's not a moon. It's going to be a dwarf planet. So they say that it's got its own orbital path, but then they say because Neptune goes into it, it means that it's not dominant in its own orbital path, so that's why it can't be a planet anymore. So that's interesting. All right, so here's Pluto and its moon, right? Here's Pluto and its moon. That's pretty cool. There's Pluto and its moon, right? And then so here is our solar system, okay? And of course, it's not to scale, right? Because things are much farther apart than this. But Pluto's orbit is greatly inclined in the orbital plane of the other major planets. You can see how Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune are kind of in this plane right here, right? This like a flat plane, right? So the third dwarf planet is named Eris, right? Third dwarf planet from the sun far beyond Neptune and Pluto, previously known as previously known as 2003 UB 313 or Xena. That's cool. Why didn't they name the other one Xena? Right? That's really neat. Um, and then so officially now known as Eris, after the Greek goddess of chaos and strife. That's kind of cool. Um, Slightly larger and about 3 times further away from the sun than Pluto is. Right, 3 times further away than the sun. That's really far. Like, how did we even see that? That's really far. A highly elliptical orbit. It takes 560 Earth years for it to revolve around the sun. Wow, that's a very long year, right? Don't you wish your school years were that long? All right, so here are the dwarf planets. Oh, so a couple more. Sorry, a couple more dwarf planets. We have Humea. We have Humea and Make. That's original. And so Humea's mass is 30% of Pluto's. It orbits at about 443 astronomical units. And Make, wonder where they got that name from, right? 75% of the mass of Pluto, and it orbits at 75 astronomical units, right? So those are a couple other not as important dwarf planets. All right. So which dwarf planet lies in the asteroid belt between Mars and Jupiter? What is the answer to this one? Yeah, Sirius is actually the one. Good job. Good job, everyone. Good job. Woohoo. Woohoo. All right, so let's talk about now the outermost reaches of the solar system. All right. See, I knew there was one called Voyager. You thought I was joking, didn't you? God, you guys all thought I was joking about Voyager. I mean, and I knew about Voyager because Voyager is the space probe that was on Star Trek: The Motion Picture. That's the reason why I knew about Voyager. See, you can learn stuff from sci-fi. Just saying. Okay. All right. So there's this Kuiper belt, right? It extends beyond the orbit of Neptune and into the space of Eris, right? It consists of a cometary material other than and other small objects. We call those all trans-Neptunian objects, right? We call all those the trans-Neptunian objects, right? Many astronomers put the edge of the solar system to be about 100 astronomical units, right? And so in 1977, we launched Voyager 1, and it reached that outer limit, right? Oh, that makes so much sense. There's a show called Outer Limits. Interesting. Anyway, it reached that outer limit in 2014 of 100 astronomical units. So that's pretty neat, right? And so in 2013, it confirmed that it had reached interstellar space. Ooh. All right, so let's talk about the origins of the solar system now. See, we were talking about this earlier too, right? It's all about the origin stuff. Okay? Any theory that purports to explain the origin and the development of the solar system must account for its present form. Okay? So, according to our best measurements, our solar system has been present at its present state for about 4.5 billion years. Wow, that's a long time. I mean, when did the dinosaurs like go extinct? Like 65 million years ago? So way longer than that, way before that, right? Billions instead of millions, right? And a valid theory for the formation of the solar system must be able to explain the number of major properties of our solar system. Something tells me that we're going to go through those major properties next, right? I'm just gonna throw that out there, okay? So there we go. Major questions concerning the solar system: origin of the material, forces that form the solar system, the isolated planets, circular orbits, and the same plane, right? Revolutions in the same direction, must rotate in the same direction, except for two, right? Terrestrial versus Jovian planets, origins of asteroids, and origins of comets and meteoroids. Interesting, right? Interesting. So let's talk about the formation of the solar system. We think that it began with a large swirling volume of cold gas and dust rotating, right? Also known as a solar nebula, right? So if you watch a lot of Star Trek, the Enterprise is always going to hide in a nebula to get away from the Klingons, right? That's what that is. Okay. I don't know if they talk about nebula a lot in Star Wars, though. I don't think I've ever heard of a nebula in Star Wars. But see, Star Wars is not as scientific as Star Trek is. I like them both, though. Contracted under the influence of its own gravity. Contracted means getting smaller, right? Getting smaller into a flattened, rotating disk, right? And then further contraction produced the proto-sun. I see, yes, a proto-star, right? Proto-sun, right? So we have a baby sun, very cute, right? Uh, this big, okay? And eventually accreted the planets, right? Accreted the planets, okay? As particles move inward, the rotation of the mass had to increase to conserve angular momentum, like an ice skater bringing in into her arms. So remember when an ice skater is spinning around and they have their arms out, they're spinning at a certain speed, but when they bring in their arms, what happens? They get faster, right? So the same thing happened here with the solar system. Okay, same thing happened here with the solar system. Because if you don't conserve that angular momentum, the planets will just start crashing into each other, right? Just like a skater would crash into the ice, right? So you got to conserve that angular momentum. Make sense, right? And I've crashed into the ice many a time when I've ice skated before, right? Now, you don't think that I could be an ice skater, right? But I'm not a very good one, though. So anyway, so here's the formation of the solar system in picture form, right? We start out with this here, right? This ball of gases and stuff. It starts to it starts to contract and get organized. Planets started getting accreted right here, right? We get flat here, and now we have our solar system. And you can see how the angular momentum is being conserved, right? Angular momentum is being conserved, and that's why we spin. It's cool stuff. Cool stuff. So, which of the following is not true about the formation of the solar system? It began with a large swirling volume of gas and dust, right? A nebula, right? Oh, sorry, I may have given that one away. Contracted under the influence of its own gravity, right? Further contraction produced the prosun and accreted the planets. Or as particles move outward, the rotation of the mass increases to conserve angular momentum. How many more slides do we have? Oh man, we're almost done. That's so sad. That's so sad. Any guesses to what the answer is here? Yes, the answer is indeed D. That's my spinning, you know, spinning ice skater thing. Whoa, got a little dizzy there. Sorry. But yes, how do ice skate? I must have asked this question before, but how do ice skaters not get dizzy when they're doing that? Right? I mean, I just got dizzy spinning around like twice just now. So As particles move outward, the rotation mass increases to conserve angular momentum? Absolutely not, right? They have to move inward to do what? To conserve angular momentum, right? They have to move inward. Good stuff. Okay, so other planetary systems. Excuse me. Are there other planetary systems in the universe? If so, we would expect to find some of these systems in different stages of formation. In other words, we should be able to find clouds of gas and primordial just old means old, right? Nebula, right? Protostars or suns and etc. We should also be able to use gravitational effects to detect small wobbles due to the rotation of objects. These are all called exoplanets or extra solar planets, right? So in Greek, the word exo and the word extra, right, means outside, right? Um, and so things that are outside our solar system that we don't have not discovered yet, right? They're called exoplanets or extrasolar objects, right? Because it's our solar system. It's kind of like when the it's kind of like when the second Constitutional Congress happened, and we made our Declaration of Independence, right? They called it an extra legal document because we were declaring independence against the king, uh, King George III, right? So they called it an extra legal because it was outside the law, right? Outside the law. Yes, 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 yes. See, I brought in some history there too, yeah, right? Vessel of knowledge. Not all of it useful, but still there, right? So let's talk about gravitational effects for a second, right? A star with a large planet orbiting about it will have a small wobble superimposed on its motion as a result of gravitational effects. This change in motion, the wobble, right, is likely due to very slight, but some cases may be detected as a Doppler shift in the star's spectrum, right? So as a star approaches the observer, the wavelengths are compressed, which is called a blue shift, right? And as the star moves away from the observer, the wavelengths are lengthened, called the red shift, right? Called the red shift. Interesting, 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 interesting. Okay. Oh man, we're coming down to the end of it here. There's like 2 slides left, 3 slides left. Okay. So the amount of wobble can be used to determine the planet's mass related to its gravitational pull. The wobble cycle time can be used to determine its orbital period, right? And so once the orbital period is known, you can use Kepler's third law, right? T squared equals k r cubed, and then you can use that to actually determine the planet's average distance from the star. You ever wonder how they know how far things are from the star, from the sun, and stuff like that? For any star, that's how they do it. All right, good old Kepler. So this is a picture of star wobble. So yeah, here's your literally it's wobbling star. The light is wobbling, right? So wobbling is illustration, but it's greatly exaggerated, right? But yeah, that's a wobbling star. Cool stuff. Um, so the transit method, right? A planet passing in front of its own, in front of its star as seen from Earth. That's the transit method, right? And so the star's light will temporarily dim, which makes sense. If something passes in front of the the sun's light, then it's going to be blocked, so it gets dim, right? And so the Kepler mission uses the transition method, the transit method, right? So the first planets discovered beyond our solar system, right, were discovered in 1992 using the Arecibo Observatory in Puerto Rico, and astronomers reported the discovery of 2 objects revolving around a pulsar. So what are pulsars? Pulsars are very dense, rapidly rotating stars, and pulsars have a very precise rotational period, right? If the rotation period is disrupted, this would indicate the presence of an object rotating around the pulsar, right? So these 2 objects are the first planets that we detected beyond our solar system. Interesting, interesting stuff. All right, these 2 planets right here. I wonder if they named them. So there have now been approximately 500 planets detected around other stars, and Kepler is finding even more and more. So these findings strongly indicate the existence of many other planetary systems in the universe, right? And so scientists are also searching for signals, right, from the universe using the extraterrestrial, so extra meaning outside terrestrial, right, intelligence, also known as SETI. So equipment today is being used to scan a wide frequency of ranges over the vast sky, right? So if I ask you on a test, what did SETI do? It detected aliens, right? During Independence Day, right? Remember that, okay? Not the actual holiday, but the movie. Okay. All right. I think this is actually our last slide. It is our last slide. I'm so sad. All right. Did someone just say you woohoo? Seriously? Seriously? I'm glad I didn't hear that person or know who said that. Which of the following is not true about the planets beyond our solar system? The first two objects were discovered in 1992, revolving about a pulsar. There's approximately 500 ones now. And then scientists are also searching for signals using SETI, right? This is an easy one. I guess I wanted the last question of the entire semester to be easy for you. And stuff. Wait, before you leave, what's the answer? D. All right. Good job, everybody.